All right, so let's look at some modifications to the idealized BJT structure which can improve performance. So the first one, if we have a single crystalline wafer, the very shallow N++ region, and again we'll assume N++ P plus N. But we add to this very shallow emitter region some polysilicon, so polycrystalline silicon. So this polycrystalline silicon is going to become part of the emitter, but its transport properties are different. So the mobility is quite a bit lower, and typically the minority carrier lifetime much lower also. Now what this means is that the minority carrier diffusion length is smaller in this layer. So let's look now at the distribution of excess holes in the emitter region. So this is the depletion width between the emitter and the base. So if the entire emitter region, let me actually change the color here. If the entire emitter region is crystalline, or designated by the X there, you have a certain slope to the to this plot, because we're plotting the delta P on a log scale versus distance. Now if we break this emitter into two parts, if we break it into a very thin single crystal region and then a thicker polycrystal region, we'll have something like this instead. So the requirement to match currents at the heavily N++ to polycrystal to single crystal junction means that the excess hole concentration has to take on a shape like this, and because the minority carrier diffusion length is much smaller in this case in the polycrystal than in the crystalline case, it has to drop much faster. Now what this means is that the slope of d delta P dx is smaller, and so the back injected hole current into the emitter is reduced quite a bit too. So this means that our injection efficiency is higher, and thus eventually we see that the alpha and beta gains are also larger. So it's an interesting effect because placing a layer not at the interface between the emitter and base, but rather slightly remote from that interface, but within the diffusion length for the crystalline material, can make a very large difference. So this is a nice technique for making the emitter injection efficiency higher. So this next subtopic is heterojunction bipolar transistors. I'm going to take it, the last one, second here. So the reason is because it has to do with the same strategy of trying to increase the ratio of electrons injected. And it's sort of a way to increase the the overall gain by heterojunction engineering. So what we're going to imagine is a n plus p junction, but now made out of type 1 heterojunction. So a typical one would be, gallium arsenide as the base and AlGas as the emitter. Now, in forward bias, when we analyzed heterojunctions, the ratio of currents is given by the offsets in the band gap. So the fact that we have a positive band gap offset means that we'll inject a lot more electrons this way in forward bias compared to holes this way in reverse bias. So we can understand this a little more if we look at the equilibrium band diagram. So there's the Fermi level, and let's draw in first the gallium arsenide far away from the junction. And then the aluminum gallium arsenide also. Okay, so when we look at the emitter going into forward bias, what we're doing here is injecting electrons through this small spike, but of course tunneling can help there, and the details of this band offset compared to the built-in voltage on this side will help determine where these energy levels line up. Now on this side, the main point though is that holes face a large barrier. And because they face such a large barrier, it means that that the back injection efficiency is greatly reduced, and in fact exponentially by the by this valence band offset. Now I'll mention another thing having to do with the use of heterojunctions. Remember, we saw band gap narrowing as a result of the very heavy doping in the emitter. And the effects of band gap narrowing can be mitigated simply by making the band gap larger in the first place. So the Ni squared for materials like AlGas are completely, just many orders of magnitude smaller than those for silicon, having the same degree of band gap narrowing. So basically 100 millivolts compared to 1.7 eV is a lot smaller than compared to 1.1 EV. And thus, the heterojunction engineering of bipolar junction transistors in making HBTs can realize quite a lot of performance gains compared to ones implemented in a single material. Okay, for our final topic and subtopic, let's go back to the silicon-based BJTs, and let's look at what happens if we put some germanium into the base. So we're going to imagine that we can construct the base with some germanium added through the base and a little bit into the emitter. So this is our germanium. So it has to be non-uniform in this design. Now we keep the same doping throughout. So we dope the usually boron into the entire structure. Entire base structure. And of course our emitter is over here. So first, what does this do in terms of the bands? So just looking at the conduction band here, because we'll again assume a NPN structure, the germanium will reduce the band gap versus distance. So the blue here is no germanium, the dashed is with. So the first effect that I'll mention is the obvious one you can see from here, which is that the presence of changing band gap versus distance induces a pseudoelectric field. And this pseudoelectric field is going to help us with collection into the collector. So the base transport factor will get better because the transit time is decreased, sometimes by a factor of up to a few, maybe 2.5. But there's also an effect having to do with the Ni as a function of distance. So because the band gap is narrowing, remember that the intrinsic carrier density Ni is going to increase. So I'll try to draw that here below. So in the presence of this germanium gradient, so if this is Ni for the no germanium case, Ni increases in this case. Now, what this means is that right at the boundary where we're going to evaluate the collector current, the Ni is larger than it is in the case with no germanium. And this means actually that the collector current will be greater than the case where there's no germanium. Now, on the other hand, the current in the base is going to remain about constant. And those two things put together means that our current gains are going to increase. So again, our alpha goes closer to 1, and our beta is increased. So the addition of a small compositional gradient can be used just like it can be in MOSFETs in order to increase the performance. Now, however, the MOSFET effects had a lot to do with mobility enhancement, whereas the BJT effects have to do with manipulation of the band diagram and the minority carrier and the intrinsic and minority carrier distributions. Okay, so let's wrap up. In this section of the module, we've looked at some structural and design changes that can be made to BJTs in order to increase their performance. And these are not entirely obvious effects, but can be used to great effect in terms of increasing the gains of the transistors. So the polysilicon emitter, the addition of a low mobility, low minority lifetime layer on purpose, but removed from the interface with the base, can actually realize gain enhancement because it decreases the slope of the minority carrier curve inside the emitter. We then talked about HBTs, or heterojunction bipolar transistors, and the application of band gap engineering and heterojunction engineering to bipolar transistors has allowed much higher gains than could be implemented inside a single material like silicon. And then lastly, we talked about some effects having to do with, again, changing the material, but in this case not making sharp layers, but rather gradients of band gap by the addition of by the addition of germanium to a silicon transistor. And all of these effects, in the end up making the gains higher and thus the transistor performance greater.